two small spheres, each of mass m and positive charge q, hang from light threads of length L. Each thread makes an angle theta with the vertical as shown below. A. On the diagram, draw and label all the forces on the right sphere. So I'm just going to quickly draw another diagram here. That's supposed to be the same, but I can't draw on this one, so I'm just going to draw another one to say that these have the same mass and the same charge. Now, they're both positive charges, so they're going to repel each other. So this is theta, and that is theta. This is L, that is L. We need to draw the forces on the right sphere. So, right off the bat, you can see that there is a string. They're hanging from light threads, and this is pulling it up with a tension force T. Right? And then, of course, you have the force of gravity. It's pulling it down. It is a bit squished, but just know that the force of gravity is pulling it straight down. And then here, we also have the electric force that is repelling it from the other sphere and causing it to move to this angle. So that's the electric force. And one more thing to note, this tension force is at an angle with theta. And again, you can prove this using alternate interior angles. You have two parallel lines here. So these two are the same. And then, so here, pulling it straight up, opposing the force of gravity, you have the tension times the cosine of theta. And over here, pulling it over, I'm going to try to erase a little bit here. So that's t cosine theta. Now over there, pulling it back towards the other sphere, you have the tension force times the sine of the angle theta. And these are going to be important when we set up our equations. Note that this is going to be the exact same for this ball as well. It's just going to be pointing in the opposite directions. Their magnitudes are the same since these two are basically have identical conditions. So first off, we can set up an equation vertically for this. We can say that the tension times the cosine of theta minus mg must equal 0. This stems from Newton's second law, where the net force is equal to the mass times acceleration, but in this case the acceleration equals 0, so this whole left side of the equation equals 0. So by moving that around, we get that the tension force times the cosine of theta is equal to the force of gravity, or the sphere's weight, mg. And that's our first part here. And so that's A. And B tells us to develop an expression for the charge Q in terms of ml, theta, g, and the Coulomb's law constant, or K. If you remember, the electric force is given by the Coulomb constant times the two charges divided by the distance between them squared. So we need to find an expression for the charge Q. And right now there are two charges, but it's given in the problem they both have the same positive charge Q. So this simply becomes Q squared since they have the same charge. And then we just need to solve for Q squared. So note that we can say that the electric force is equal to Coulomb's constant times Q squared divided by R squared. But we can't really solve for Q because we can't use this to represent the charge. So we need to use our second equation. Remember this guy, T sine theta, that's pulling it back and opposing the electric force. We can say that the electric force minus the tension times the sine of theta is equal to 0. Again, because these are not moving, it's making an angle. So we're assuming that it's already settled and is at rest. So from this we get that the electric force is equal to the tension times the sine of theta. And that's good news, because we can substitute this back into this equation. So if I make a little bit more space, we get that the tension times the sine of theta is equal to Coulomb constant times charges squared, q squared, divided by the distance between them squared. So that's one part done. Now, we still can't do anything yet because we need to put it in terms of m, l, theta, and g. So, we still need to find a way to substitute the distance between them. And this actually isn't that hard. If you look back to this, you can see that the distance is just simply, the distance between them is simply this part. And that makes a right triangle here. So if this is L, and that's the angle theta, this would be L times the sine of theta. And then this would be the same thing, it's a mirror version, L sine theta. So together, these two would make 2L the sine theta. Sorry if it's a little small, but the total distance between the two spheres would be 2 times the length times the sine theta, which you can find using some trigonometry here. So we can replace that with r equals 2 times L sine theta. So r squared is equal to 4L squared sine squared theta. And that can be used to replace that here. So we get the tension times the sine of theta is equal to Coulomb constant. I actually probably should move some stuff around a little. So if we multiply this by r squared, divide that by k, we will separate the charges all to one side. Again, I'm just simply manipulating the equation a little there. So, and then we can replace r. So we know that the charge squared is equal to the tension times the sine of theta times sine theta times 4L squared sine squared theta. Remember, that was the distance squared between the two spheres. And we're going to divide that by the Coulomb constant here. Okay. Gonna get rid of everyone else here. But we're not done yet, because it doesn't say we can use t in our expression. So we need to solve for t, which was why this equation came in handy. From this, we can say that the tension is equal to the weight, mg, divided by the cosine of the angle theta. And then we can substitute this in again. So, you can say that the charge squared is equal to mg divided by cosine theta times sine theta times 4L squared sine squared theta. I can actually move the sine out to make sine cubed theta times 4L squared. And then just divide that whole thing by the Coulomb constant. It just stays there. So now if you recognize, you might remember that tangent of theta is equal to the sine of theta divided by the cosine of theta. So we can take one of these sines and divide it by cosine to get tangent. So the charge squared is equal to the weight times the tangent of theta times sine squared of theta times 4L squared, all divided by the Coulomb's constant. Okay. So let's erase some more. And now all we need to do is just square root that whole side. It's equal to square root of mg, that whole expression there. So this is literally what I just wrote, but I am going to show this step here. So now we can erase this. And now we can simplify this by taking like some of this stuff out of the square root. So our final expression, we get that the charge is equal to 2L remember we can take this out. That's the distance squared, so we can square root it. Times the sine of theta, again we have a sine squared, times the square root of mg times the tangent of theta, divided by Coulomb's constant, K. And that is how you would solve this problem here.